Okay, are there any questions? Okay, we continue with the assignment. We had to prove that so it's clearly a vector identity. B plus C is a vector, and cross product of that with A is also a vector, and you have two vectors on the right hand side. Also, if you look at this, you will see the direction of B cross C, as we have said. Let's say we have B and C like this. The direction, let's say this is the plane of the vectors B and C. We have seen that the cross product is, the direction of it is in the normal to the plane formed by the vectors B and C. Right? So, if you look at this, it's somewhat interesting. So that is this. The direction of this is the direction normal to the plane B and C. A is now any arbitrary vector. Now if you take the cross product of that, which I have here, is pointing out of the plane, any vector, what can you say about the right hand side? B and C. It's a linear combination of B and C. So on what plane does it lie? Plane formed by B and C. If you look at Aris, for instance, he says A and B are two vectors, and alpha A times plus beta B is the, will give you any, all possible vectors in the plane formed by A and B. So what you seem to be getting is that when you take the cross product of B cross C, any arbitrary vector, it projects that pointing out, the normal pointing out of the plane, projects it back into the plane. That's sort of the interpretation that we can give. Proof of this is, I can write this as A cross D as we saw. So I have an I component of the left hand side, A J D K, where D is C cross C. So if we want the K component of this, we saw that I could write this in an analogous way. So I start with K. So I start with epsilon I J K. This would be K. We cannot use either I or J, for that matter K anymore. So we have to use two other indices, and that would be B L C M. So the left hand side, the I component would be epsilon I K, epsilon K L M. Some of the J, K, L and N look quite complicated, but thankfully there is this identity which again is there in Aris, we have just borrowed. We had to prove this. So what you have, you can easily verify by simply choosing various values of but what you should understand is only a sum over K. So it's actually dependent on four indices, I, J, L and M, this alone, not about the rest of it. So what you will get is the deltas will come in, thereby making this very easy to handle. Delta I L, delta J M minus delta I M delta J M. The product of two chronic and delta functions. So again, left hand side I component can now be written as delta I L delta J M A J B L C M minus delta I M A K B L C M. J, I mean not sum over I, but L, J and M. So I have to make I equal to L, or rather L equal to I, right? So, and then J is equal to M. So what would become of that? I equal to L, so I get I, A, J, C, J. No sum over I. So what I have reduced is the sum over J, L and M has been reduced to a sum over J alone. And then I have minus. Here I have I equal to M. This will become Ci. And then I have AJBL. Then we have JL. I can either write this ALBL or AJBL. Doesn't matter. J must be equal to L. So have we now got the answer? We have got the answer because when you look at the ith component, the ith component of the left hand side, AJ is nothing but A dot C. The ith component is A dot C times Bi minus AJ Bj is A dot B times Ci. So this is the ith component. So clearly the vector identity is proven because I've taken an arbitrary component, ith component. And so I can now, from this, I can simply conclude that this is true. Right? So the critical point here is being able to use this. That's the main purpose of giving this. It simplifies considerably. Now you have another closely related problem if you see. To prove that A belongs this is now a scalar identity, right? Now a scalar identity. So can you use what we have derived here and prove that? You can use this, right? So, yeah. No, that is identity I wanted you to use. A cross B cross C I have. So what does C become equal to here? A. So I have to substitute C equal to A. Good. Yeah. Minus A dot B. A. No, the whole thing you have to put within brackets. Exactly, yeah. Now what is this? That's a vector, so you have to put an underscore on all the vectors. Yes. A dot A, that is A dot A times 1. No, A dot A is not 1, because it's a unit vector. Right, so, but you have to prove only that that is 0. That's not equal to B. What is the first term? You have A dot A B dotted with A. A dot A is just a scalar. Right? It's not equal to 1. It's just A dot A. If you want, you can write it as, mod, the length of A square. Mod of A square. Yes, that's equal to 0. That's what you have to do. Right? B dot A is equal to A dot B. Because it's just a scalar dot product. So you prove that that is equal to B. The fourth identity also. I'll let you do the problem 3, subdivision 3 in the first problem, A cross B dot C cross D. Very similar to this. You again will have epsilon ijk for A cross B. And then C cross D you have to probably use epsilon K again or whatever. It will be very similar. I'll let you prove that on your own. Right? Some of you may have tried and proved it. Right? What we will now get into is some important relations. We have already proved phi, right? 5 we have already proved in the previous class. 7 is, I have already used it. So we used it to prove whatever. 7. Right? Now here A and B are different. In that case A and B were both equal to B. But here they are different. Right? So we prove whatever it is. You put A equal to B equal to B in the identity that is given, that is 7, you will get the result that we which we have proved also. Right? So that's again fairly straightforward. It's just a generalization of the case where the two vectors are not equal. So you should go ahead and prove it. What I want to point out is some very important relations which maybe not that difficult to prove, but which we will be using later. This is striking relation. You look at 6. There are many ways of doing this. So this is a scalar identity. The divergence of a vector, which in turn is a curl of a vector, is equal to 0. And then the curl of the gradient of a scalar is 0. This is now a vector identity. So what is this? The important thing here is A, the vector A and the scalar phi are arbitrary. What this says really, better way of writing this is divergence of curl of A is equal to 0 and the curl of the gradient of a phi, which is scalar, is equal to 0 vector. No matter what the scalar you start with, if you take the gradient of that and take the curl of the resulting vector, you will get 0. That's what we have to prove, right? And this is another identity. What it says is take the curl of any vector, arbitrary vector, and take the divergence of the vector that comes out of that. The result will be 0. We have to prove this. Now let's proceed. Let's start with this, right? Divergence of a vector, right? So I can call, for instance, so many ways of doing it. Let's say I'll call this, right? So can you do this? Aris. You can do whichever way you want, but maybe I have started in a certain way. It will help you do it. You have to get used to. So now, first write the divergence of B. What is the formula? What I give you the formula sheet. Divergence of a vector. So now write this is so right hand side is divergence of B. So write what is equal. By now, as you go along, you should not be really, at least for some of the basic expressions, you should not be looking at the formula sheet, right? So you should get, yes, good, yeah. So now write B. What is B? The curl of A. So I want the ith component of the curl of A. That's there in the formula sheet. The ith component. So Bi, right? That's a curl of A. The ith component of B is given in the epsilon. It will involve an epsilon. I-A-K, yes, A, K, comma, J, and then the whole thing would have to have a comma I, right? That's fine. So now what you are having is, so it might be just easier to write this. So you've got two commas. So if you want, you can shift back to the partial derivative. Okay, now hold on, yeah. Write this. fill in the details. X, you can write whichever way you want because it's a mixed partial derivative. Dx, j, and then xi. Right? Yeah, that's fine. You can leave it there. Now, what I want one of you to do is actually, now this is the sum over all the three indices. This is actually a scalar identity. Right? So now, can you write out the sum? This is an exercise. It's possible actually to prove. Can you write out the sum fully? I equal to 1, j equal to, I equal to 1 to 3, j equal to 1 to 3, k equal to 1 to 3. But you know, all terms are not going to come because I can choose I equal to 1, right? And I have j equal to 2 and 3, right? So let's just erase this. Okay, I want you to write first. So you write for I equal to 1. I equal to 1. There will be only how many terms will come for I equal to 1? 2 terms. Write those 2 terms. No, write it as partial derivative second. No, just second order. Yeah, d square. No, you would take it would be okay, that's fine. Fine, leave it. So let's have somebody write I equal to. Okay, fine. Yes. Somebody write the term from someone from behind. When you come forward, this is not 0 as yet. You have to write all the 3 terms before you conclude that this is 0. Now write the I equal to 2. I want you to write the 2 terms. You should get familiar with manipulating or writing out the terms properly. Or 2, 1, 3, I equal to 2. Okay. I equal to 2. Yeah. J and I, whatever J you have chosen 1. Yeah. Chosen J equal to 1. So, but then K equal to 3. Yeah, but you can't have that. It's not x3. Just carefully do it. I and j are to come, right? Minus. Okay, plus. 2, 3, 1. Be a bit careful. It can be a bit confusing, but you have to keep. A1. Okay, now can you write what is the sign of this? 2, 1, 3. Minus, is it? Yeah, 2, 1, 3 is minus, yeah. And 2, 3, 1, obviously plus 1. Okay, good. Yeah. So I equal to 3. I'll write it myself because it looks like you're getting the hand of this. So I equal to 3. Right? Will be epsilon 3, and then j has to be 1 or 2. If I choose j equal to 1 and k to be 2, right? So I get d squared a2 k. I and j have to come, and I can write it whichever way I want, right? So d x1, d x3. That's sort of interchange. You don't interpret it exactly. I'm not. Plus 3, 2, 1. So I still remains as 3, right? But now k has been made 1, right? So I dx3. So this is 3, 1, 2 is plus 1, and this is minus 1. So you can now see that all the terms are cancelling. D squared a3 by dx2 minus. So this is cancelling with this, and this is cancelling with this, and this is cancelling with this. And so the whole thing is 0. But if you want to do it with, without writing it out, there's another way that was suggested when you taught the course last time. If you look at this, there's some similarity between the cross product of two vectors and the curl of two vectors. Right? We have already seen. I'll just illustrate. Suppose I take D cross C, right? And that I will write this as epsilon I j k b. If you want, I can write this as epsilon I j k e I b j c k. Now, if you take the dot product of, we've taken what happens when you take the cross product of another vector with this. However, if you take the dot product, right, you can easily show that this will now be a scalar. It's called as a scalar triple product, right? And it can be written as epsilon I j k a I b j c k. That is nothing but a1, a2, a3, b1, b2, b3, c1, c2, c3. Now, the same way we have seen the curl of A can be written as epsilon I j k, right? A k comma j e I. Or a better way to write this is epsilon I j k d by dxj, or rather ei d by dxj a k. So from this we can easily infer that this can now be written as e1, e2, e3, right? D by dx1, d by dx2, d by dx3, and a1, a2, a3. What are these? A1, a2, a3 are components of the vector A. E1, e2, e3 are the unit vectors along the 1, 2, and 3 directions. Right? So it's a vector that comes into this. Now, in the same way, I could argue, and it's actually easy to prove, that this would be given by, right, d by dx1, d by dx2, d by dx3, again d by dx1, and a1, a2, a3. Of course, the argument is that two of the rows are the same, somewhat misleading here, because these are operators. Because you can conclude from this by looking at it that because two of the rows are equal, right, the determinant must be 0. But actually that's somewhat misleading, because actually then it seems like we have not made use of the crucial point here is the equality of the mixed partial derivatives, right? So of course this one would be 0, but it is not becoming like also to understand that when you, for instance, how would you write this determinant? You can easily probably show that this is what this would turn out to be. The even will not come, that's what I am saying, because the net result is a scalar. Because I am taking the dot product, I am using the analogy, it's possible to prove this, right? So d by dx1, because it's not just multiplying d by dx1 and d by dx2, it is sort of the impression you get when you say two of the rows are equal, so that sum has to be 0. If I write this d by dx1, now what would you do, right? This is d by dx2 a3, right? by dx3 a2. That's what you will get. So that is d squared a3 by dx1 dx2 plus d squared a2 by dx1. Oh, I'm sorry, minus. And then you can write out the entire set of terms. There are so many other terms. Minus, then you can do this like you're writing a regular determinant, right? But you have to know that you're operating. This is an operator. You have to operate on something. You cannot just leave it, hanging, waiting to be operated on something. On something, right? So if you understand that, when you write it like this, it's clear that to prove that this is zero, you have to use the equality of mixed partial derivatives, which of course is very clear here. We are doing the same thing. Here it is in the form of epsilon ikk. We are still writing the determinant only, right? But there it is more easier to write because you all know how to calculate the determinant directly from the variables. That would also lead to the same answer. You again get 6 terms with a 3 by 3 determinant, 3 by 3 matrix, 3 factors of terms, 6 terms in everything. Finally, add up to 0 because of the equality of the mixed partial derivatives. If you want to just work on it here itself, if you want to do this here, that also is possible. Epsilon ijk, I have ak, comma g, comma I. Right? You have to there might be a way to do this because in ak and then I have comma j, comma I, so I can write this as epsilon ijk ak comma I comma j. How are you going to prove that this is zero? That's an interesting exercise without expanding it out, right? How would you prove it is zero? Basically, what I would have to prove is that epsilon ijk comma j comma I is equal to the negative of itself. If I am able to prove it, right, then that is zero. So I am starting with this. I have now done. Now what should I do? I can now interchange indices I and j here, right? I can interchange indices I and j here.
Won't this just be negative of the earlier?
No, or I can interchange, yeah, that would be the negative. Yeah, what I can do is interchange I and j throughout, right? Interchange I and j throughout. Then I get this equal to epsilon j I k, ak comma j comma I. Interchange I and j throughout, then the sign doesn't change. We have already seen. And this, instead of putting j equal to 1 to 3, I equal to 1 to 3, I am saying I equal to 1 to 3, j equal to 1 to 3. That's perfectly valid. Nothing is going to change because these are just dummy indices of summation, right? So now I see here I have epsilon ijk. This is fine. Ak comma j comma I. That is fine actually. But here I have epsilon j ik. Here I have epsilon ijk. So if I want to bring it into that, I have to interchange indices here. Only here, right? Because basically again throughout, there's no point. I have started. This would be minus epsilon ijk ak comma j comma I. What I have shown is that epsilon ijk ak comma j comma I, which is what this is equal to minus epsilon ijk ak comma j I, which implies that epsilon ijk ak comma j comma I. See, each method has, this is probably the most sort of a brute force method, just expanding it out and then verifying it, see it's perfectly fine. That one brings out, the dot product of a cross product, the operator in base instead of just the cross product. The similarity between the curl of a vector and the cross product of two vectors on the one hand, and scalar dot product, or what is called as the scalar triple product. Something to that effect, I am not very sure of the name, but clearly it is a scalar. The net result is a scalar. So I think from taking the dot product of the cross product, that will simply give the determinant. By using the similar idea, I can interpret this as the operator, dot product of the operator on a cross product of the operator with another vector. So I get the same determinant and I can argue then that is zero. Or I can simply, this is probably I would regard as the most elegant because maybe the most instructive because it helps you to understand the way to manipulate the indices in a summation. Right? Somewhat maybe not very obvious how you would do it, but at each step, the principle is used. That's what I want you to understand. At this step, what is the principle that was used? No, there's no negative here. What is the interchange, the equality of mixed partial derivatives? That has nothing to do with summation or anything. Right? So equality of mixed partial derivatives. Here, right, interchange of indices throughout the sum. Then it doesn't change. We've already seen this. The interchange indices throughout the sum. Right? The sum doesn't change. That's the principle I'm using. Even if you don't quite follow how this is happening, you should first understand. Get the principle. The best way is to interchange and find out, write it out and verify for yourself. You're not able to see the argument. Here, what is happening is that interchange, because it is only in epsilon. So there we have seen, if it's an odd interchange, it would be negative. You have to change the sign. If it's an even interchange, the sign will remain the same. So that is the principle I am adopting there. So here, the third step is interchange of indices in alone. And that means I have to know how many interchanges I am doing. If I am doing an odd number of interchanges, then I have to make it negative of what I started off with. If I am doing an even number of interchanges, then I have to retain the same sign. So then I finally get to the final step. So each method has its, so it teaches you something. So I want you to just think over it and try to understand what we have done. So I leave the next part for you to attempt and do whichever way you want to do it. Finally, the answer is zero. So I don't know what principles will be used there. So I will let you do it. We've almost come to the end of the assignment. I will just do problem 9 and leave problem 10 for you to do. Only thing problem 10 has the Laplacian, which probably many of you already have seen in your courses on heat transfer or fluid mechanics. So the 10th, I will let you do it yourself. All of these expressions, especially probably 6, 7 we have already used earlier. I'm not very sure about the others, but certainly 9 and 10 will be using it later when you're dealing with the rotational flow. Right? So these are important to later on we encounter. So I'm just doing this for arbitrary vectors. So I'll just explain. This is a vector this is the gradient of the divergence. That is not zero. Gradient of divergence will give you a vector. First of all, this is a vector identity. The curl of the curl of a vector, that is not zero. That is all in general, right? And then you have the Laplacian. It's a scalar. I just write it what because we need only the rectilinear Cartesian coordinate. That is that's the Laplacian in rectilinear Cartesian coordinate system. Right? So that is often also written as the dot product of the inverted Laplacian, which is sometimes maybe you can call it the gradient operator with itself. Right? So the way to verify this is I write this as d1 dy dx1 plus so on. I take the dot product with itself. So clearly, only e1 dot e1 will give me d squared dx1 square, e2 dot e2 will give d squared dx2 square, and similarly e3 dot e3 will give d squared dx3. So all the other terms will be zero, right? So that's another way of writing that. So I'm not going to derive this or prove this, but I just take this, the ninth one. It's very similar. The two are similar. Do one on the board. Maybe some of you can come and help. But the other one I'm letting you try it on your own. It's probably more difficult to prove than the 10th one. It is clear that this is what is the equation. It's a scalar equation or a vector equation. Scalar. Scalar. What is the curl of the vector? It's a vector equation. You should not have such doubt. Write it here, scalar. Some of you will hesitantly say scalar. You cannot have such hesitation. Of course, again you are hesitating. You are very forthright. This next scale, that's another point. But you have to see what is each term, how it is a vector. It's the curl of a vector. So that's a vector, right? Cross product of a vector, the vector is a vector. So sometimes you have to be careful. There could be some typos or misprints in a book or something. If you're not sure whether what is written, right? So this is clearly the gradient. It is operating on a scalar. A dot A is a scalar, right? The gradient of a scalar is again a vector. So it has to be a vector throughout. Now this one is the dot product of a vector with a tensor. So you can see each one of them is a vector. They are all coming out of different sets of operations. This is come out of the curl of a vector and then a cross product. This is coming out of the gradient of a scalar. The third term is coming over a dot product of vectors and a tensor. So you get to use a fair number of the operations that we have had, right? Where the right hand side would be easier to use, do first. I'll do that because we won't have time. This one, you can see there's an epsilon ikk here. There's also an epsilon that will come here. So we get to use that same epsilon ikk, epsilon k, and something like that we have to use. So let's first write down the gradient. Suppose so it's a vector equation. So I'm going to proceed in my way, and the I component of each term. So first I want you to write the I component of this I component. Can you just Lokesh Kumar? I component of the gradient of the dot product of A with A. Formulation can see. How would you write it? It's not as straightforward as you might think. component. I have already told you. You don't have a choice. I can do the same thing in an exam. Right? I can ask you, force you to write the ith component, and you cannot use I as a summation index. So you cannot. It's not just about doing it whichever way you are comfortable. You also have to be comfortable with the way I am comfortable doing things. That's the problem. Yes, you cannot do this. I want the ith component. So A dot A. AI is not, you cannot use I as summation index because I want the ith component. So if you are not following it, then you have not understood what I have been saying all along. AJ, yeah, that is better. Yes, AJ, the gradient of that, the ith component, what is it? AJ comma I, yes, it's not complete. It's not complete. Okay, you're having a problem writing this. Let's see how, yes, quantum. That is correct. The gradient of AJ, that is fine. Now write the ith component of that. The ith component would be the derivative of that. What is the ith component? The gradient of phi comma I. So I want AJ comma I. All, that's how you have to calculate. You can understand what comma I means. Yes, I already written one term. Part of one term. Product rule, yes. Slowly running out of time. I don't want the cross product. I want the gradient of AJ. Do you understand it or not? Yes, he's already taken the gradient. Yes, now come. No epsilon, he's not following. Yes, you can come back and write. That is fine, yeah. Yeah, that's fine. Yeah, I think that is correct, but I would have preferred to have written it this way. Right? Anyway, you had the right idea. So you just have to differentiate. The important thing to remember is that you cannot, this is tempting to write this as AJ squared, for instance. That is, it is not. That's what you have to understand. This one is not equal to AJ squared. I mean, because you're using the summation index, repeated summation index convention. On the face of it, you might think that I'm, doing something totally against what you have learned in high school. After all, if I give AJ times AJ to any high school student, you simply write this as AJ squared. Perfectly justified in doing it. Graduated far out of high school. So now suddenly AJ times AJ is not equal to AJ squared, right? Because it defeats the whole purpose of having the repeated index summation convention. AJ times AJ is A1 squared plus A2 squared plus A3 squared, right? And AJ squared has no meaning in itself. What is J? Right? We want to represent A1 squared plus A2 squared plus A3 squared. Simply write it as AJ squared, you don't get anything out of it. This is correct. So we've got one of the term. You can try to fill out the other terms. We do that, complete it in tomorrow's class, and then move on with other things. If there are no questions, then I will just end for today.